This is a continuation of the preceding clip, which was interrupted by a technical malfunction. We were integrating f dot ds for f of xy equal this function on an arbitrary circle centered at the origin. The circle was parameterized as shown. This is the a parameterization of a circle of radius a centered at the origin. Our function f is mi plus nj with m equal to the coefficient of I, n equal to the coefficient of j. And we should by now be familiar with the idea that the integral of f dot ds is this integral of m dx plus n dy. The integral is taken around the closed curve, the circle in this case, and we just substitute for m and n. Substituting for m, substituting for m, we get negative y, which is negative a sine of 2 pi t, and x squared plus y squared, as we can see, is simply a. We're on a circle of radius a in the plane, so x squared plus y squared is a. But if we substitute x equal a cosine 2 pi t, y equal a sine 2 pi t for the x and y expressions, we are going to get a squared. We get a squared cosine squared of 2 pi t plus a squared sine squared of 2 pi t. The a squared is going to factor out, and we're just going to end up with cosine squared of 2 pi t plus sine squared of 2 pi t multiplied by the a squared, and by the Pythagorean identity that just gives us the a squared. So again, the x squared plus y squared is just a squared, and we're going to use the same idea when we write down the n function. Then our dx is the differential of the x expression of a cosine of 2 pi t. And then we write the same thing down for n. The only difference is that, of course, we have an x and we don't have a negative, so we're going to use the a cosine of 2 pi t to represent x, and we'll have the a squared in the denominator, as we've seen, and then it's times the differential of the quantity a sine of 2 pi t. And all we really need to do is just write this expression, take our parameterization, plug in, and we get this expression. Now, what we need to do is we need to find the differential of a cosine of 2 pi t. That's just the derivative of this with respect to t multiplied by the dt. T derivative of a cosine 2 pi t, the chain rule is going to give us a 2 pi. The derivative of the cosine is the negative of the sine. So we get negative 2 pi sine of 2 pi t times dt. And over here, we get an analogous result. The differential of a sine of 2 pi t. Again, the chain rule gives us the 2 pi. The derivative of the sine is the cosine. And we multiply the derivative of this expression with respect to t, which is this, times the dt to get the differential. This expression is easily rearranged into this expression. We simply factor out the 2 pi's. We factor out the dt, and we have what? Sine squared of 2 pi t, cosine gives us cosine squared of 2 pi t. That's just the sum of a sine squared and a cosine squared of the same argument. So the Pythagorean identity tells us this is just 1, so that this simply becomes the integral of 2 pi times the integral from 0 to 1 of dt. Now, the integral for t goes from 0 to 1, of course, because our parameterization was for the interval 0 to t equals 0 to 1, 0 less than or equal to t less than or equal to 1. So that our final result, well, the integral from 0 to 1 of dt is just t evaluated between 1 and 0. That's 1, and that tells us that the integral is 2 pi. So we've established what we set out to establish, that the integral of this function around any circle centered at the origin is 2 pi.